In the last few lectures, we had started our discussion on forced convection. If you recall, we had done the flow past a flat surface where the surface is heated for in the region x between 0 and L, and we had determined the temperature field, the heat flux and the Nusselt number correlation for that. We had used that for calculating the Nusselt number correlation for the heat transfer in a pipe and also for a stagnation point flow. The fundamental principle in all of these is that in the case of forced convection, when convective effects are large compared to diffusive effects, you cannot just neglect diffusion, because if you neglect diffusion, there is no heat transfer from the surface, because the convective transport is only along the flow direction. In the direction perpendicular to the flow, there is no convective transport. At a surface, the flow is tangential to the surface because of the no penetration condition. Therefore, there is a flow only along the surface, there is no flow perpendicular to the surface. Heat transfer from the surface cannot take place due to convection, and therefore, heat transfer has to take place due to diffusion. In the limit of high Peclet number, when convective effects are large compared to diffusive effects, in the bulk of the flow, convection is dominant. However, close to the surface, there are thin regions where convection is comparable to diffusion, because whatever energy is being transferred perpendicular to the surface due to diffusion is rapidly getting swept downstream due to convection. Therefore, the disturbance due to the temperature field is restricted to a thin region close to the surface, and that is what is called the boundary layer, the region within which there is a disturbance due to the temperature field due to the heating from the surface in the limit as the Peclet number becomes large. In the limit as the Peclet number becomes large, the boundary layer thickness becomes small in such a way that convection and diffusion continue to be comparable in the boundary layer even as the Peclet number is increased. The boundary layer thickness becomes small, and therefore, the heat flux, which scales as the temperature difference divided by the boundary layer thickness, becomes large. We saw that for heat transfer from a surface where there is a no slip condition at the surface, the boundary layer thickness scales as Peclet number to the minus 1/3 in the limit as the Peclet number becomes large, and therefore, the flux increases proportional to Peclet number per 1/3. This was a common feature for the flow past a flat plate, the flow in a pipe and the stagnation point flow. We examined another such situation, that was flow past a sphere. That was what we started in the last lecture. Okay. So, the configuration is as follows. Okay. You have a spherical particle of radius r, okay, at the surface of which the temperature is T naught. Okay. The temperature at the surface of the sphere is T naught, and the free stream temperature far from the sphere is T infinity. Okay. And we had the velocity, the components of the velocity specified in this case. These are the velocity components for a laminar flow in the viscous regime, okay, in the low Reynolds number regime. These are the components of the velocity. Okay. So, first thing, we define the scale temperature. Okay. Okay. So, the scale temperature T star is equal to T minus T infinity by T naught minus T infinity. Okay. As usual, T minus the temperature far from the sphere divided by the difference between the surface and the temperature far from the sphere. Okay. So, that is the usual. Okay. This implies that at r is equal to r, T star is equal to 1, and for r going to infinity, T star is equal to 0. Okay. So, there is no, the temperature is 0, scale temperature is 0 far from the sphere. At the surface, the scale temperature is 1. Okay. recall that I had defined the velocity components for you, okay, in terms of the free stream velocity. Okay. It is convenient to define scaled velocities and scaled distances. Okay. R star is equal to R by R. Okay. And the velocity is scaled by the free stream velocity far upstream of the sphere. Okay. The free stream velocity far upstream of the sphere. Okay. The velocity is scaled by the free stream velocity far upstream of the sphere. Okay. So, let me V r star is equal to V r by V free stream, and V theta star is equal to V theta by V free stream. Okay. So, let me plot the sphere once again for clarity. Okay. So, the free stream velocity is incident on the sphere, okay, in what I will call the x direction. Okay. Okay. This is the x axis, okay, and you have the fluid flow streamlines going around the sphere like this. Okay. Sphere radius is r, okay, and we use a coordinate system, a spherical coordinate system for the heat transfer around the sphere, where r is the radius and theta is the azimuthal angle. Okay. Theta is the angle measured from the x coordinate. Okay. You can consider either the fluid as flowing in the minus x direction past a stationary sphere, or as a sphere moving in the plus x direction in a stationary fluid. The two are equivalent. Okay. And I have T star is equal to 1 at the surface of the sphere, and T star equals 0 far from the sphere. Okay. Here T star is equal to 0 far from the surface, and T star is equal to 1 at the surface. Okay. Conservation equation. Okay. If I scale it, as I said in the last lecture, okay, the fluid is flowing past the surface. Okay. Fluid is flowing past the surface. Therefore, the coordinate along the surface is the streamwise coordinate. Okay. The coordinate along the surface is the streamwise coordinate. In this problem, the streamwise coordinate is in the theta direction. Okay. It is the coordinate along the surface, the streamwise coordinate, it is in the theta direction. The cross stream coordinate is in the r direction. Okay. The direction perpendicular to the surface is the cross stream coordinate, which is the r direction. Okay. So, the energy balance equation in this case, the convection diffusion equation for a steady flow, okay, I had written it here for you. Okay. I had written it here for you, and I can write it in terms of dimensionless groups. Okay. So, on the left side I will have the ratio of the V free stream by r into partial T star plus V theta star by okay. On the right side I have alpha divided by r square, because I have two derivatives, there is two spatial derivatives, okay, into 1 by r star square partial by partial r star of r star square partial T star by partial r star. Okay. And I can divide throughout by alpha by r square. So, on the right side I will get just the coefficient to be 1. Okay. On the left side I will get VFS r by alpha. Okay. Note that the Peclet number is classically defined with respect to the sphere velocity or the free stream velocity and the diameter. Okay. So, therefore, on the left side I am having a Peclet number by 2, okay, into VR partial T by partial r plus V theta by r partial T by partial theta. Now, what is Vr and V theta? Okay. So, the dimensional velocities were given here, okay, and you can use these to get the scaled velocities. Okay. I will just write the scaled velocities for you. Vr star is equal to minus cos theta, let me write this, okay, into 1 minus 3 by 2 r star plus 1 by 2 r star cubed. Okay. V theta is equal to sin theta into 1 minus 3 by 4 r star minus 1 by 4 r star cube. Okay. So, those are the equations and the velocity components, and as you can see, with such complicated velocities, it is going to be difficult to solve, okay, these equations. However, we know that in the limit of high Peclet number, the effect of the heating will be restricted to a small region close to the surface. We know that the effect of heating is going to be restricted to a small region close to the surface. Okay. Therefore, we can focus our attention on this region, okay, of thickness, the boundary layer thickness delta, okay, of thickness, okay, at the surface. I have a region. Okay. So, this is this location is r is equal to r star is equal to 1. Okay. So, if I go a small distance away, right, r star is equal to 1 plus y, okay, where y is the distance from the surface, okay, where y is the distance from the surface. Okay. Therefore, y is equal to r star minus 1, okay, the distance from the surface. Okay. This is written as the product of a boundary layer thickness. So, in the scaling approximation, okay, in our scaling approximation, if you recall, we had scaled the cross stream coordinate divided by the boundary layer thickness. The ratio of the cross stream coordinate and the boundary layer thickness was the parameter eta, okay, in our similarity solution. In the case of flow past a flat plate and stagnation point flow, the cross stream coordinate was just z. In this case, the cross stream coordinate is r star minus 1. Okay. The cross stream coordinate, the distance from the surface, is r star minus 1. Okay. Therefore, this, okay, therefore, I have to define my dimensionless variable as r star minus 1 by delta, where delta is a function of the streamwise coordinate theta. In the previous cases for the flat plate flow, the streamwise coordinate was x. Therefore, I had the similarity variable as z by delta of x. In this case, the cross stream coordinate is r star minus 1, boundary layer thickness is delta. Okay. Therefore, r star minus 1 is equal to eta times delta, okay, or okay, r star is equal to 1 plus eta delta. Okay. So, that is the substitution that we have to do, okay, for the similarity variable. Okay. We have to express r star is equal to 1 plus eta delta. Okay. Delta is the boundary layer thickness. Okay. In this case, it is a scaled boundary layer thickness, because I have already scaled the radius by capital R. Okay. So, I will just use the symbol, the star, to indicate that this is a scaled boundary layer thickness, scaled by the radius of the sphere. Okay. So, this is our substitution, where delta is a function of theta. I have to substitute this into the equations and into the velocities in order to find out the equation, the convection diffusion equation, in terms of the similarity variable eta and the velocity components in terms of the similarity variable eta. Note that in this expression, eta is order 1. It is a scaled variable, it is a scaled similarity variable. Okay. It is considered to be order 1. Delta is the boundary layer thickness. It decreases to 0 in the limit as Peclet number becomes large, so that convection and diffusion are comparable within the moduli layer. Okay. So, delta is the parameter that goes to 0, eta is order 1, okay, it is a scaled variable. So, rather than work with these velocities, what we can do is to define scaled velocities in terms of this substitution for r star in terms of eta. Okay. So, V r star is equal to minus cos theta into 1 minus 3 by 2 into 1 plus delta star eta, okay, plus 1 by 2 into 1 plus delta star eta the whole cubed. Okay. This is the velocity component. We are considering the case where delta is small. Okay. You can easily see that if delta is equal to 0, which is the surface of the sphere, this velocity component is identically 0, as is required from the no slip condition. Okay. So, delta is if eta is 0 at the surface, then this is 0. We can simplify this by using a binomial expansion, that is 1 plus delta star eta power minus n is equal to 1 minus n delta star eta plus n into n plus 1 by 2 factorial delta star eta the whole square plus etc. Okay. Therefore, this term, okay, 3 by 2 into 1 plus delta star eta power minus 1 is equal to 1 minus delta star eta plus, okay, n into n plus 1. So, 2 divided by 2 factorial, okay, n into n plus 1 is 2 by 2 factorial delta star eta the whole square plus etc. Okay. Similarly, 1 by 2 into 1 plus delta star eta power minus 3, okay, that is this term here. Okay. This is equal to, sorry, I should have a 3 by 2 outside, my apologies here. So, this is just delta star eta, so it will be a 3 by 2 outside. Okay. And in the second term, I have 1 by 2 into 1 minus 3 delta star eta plus, okay, n into n plus 1, 3 into 4 by 2 factorial delta star eta the whole square plus etc. Okay. Okay. So, that the velocity, okay, the velocity here, this Vr, the velocity Vr here, okay, is equal to minus of this, okay, plus of this, okay, plus 1. Okay. And you can see that 1 by 2, okay, 1 by 2, okay, if I add 1 minus 3 by 2, okay, so so, minus 3 by 2 plus 1 by 2 plus 1, that turns out to be 0. The second term, these two also sum to 0. You have plus 3 by 2 delta eta minus 3 delta eta, that sums to 0. Okay. And I am left with these two terms here, okay, 3 by 2, okay, and 6, okay, 6 by 2. So, that is 3, okay, 3 by 2 and 3, that is 6 by 2. Okay. Okay, times minus cos theta here, okay, times minus cos theta. So, basically if you add up all of these, you will get this is equal to minus cos theta, okay, into 3 by 2 into delta square delta star square eta square, okay, if you expand it out. So, that is the leading order term in an expansion in small delta. Okay. This is the leading order term in an expansion in small delta. Okay. And now we need an expression for V theta. Okay. V theta star is equal to sin theta into 1 minus 3 by 4 1 plus delta eta, okay, minus 1 by 4 into 1 plus delta eta the whole cubed. You have to do a similar expansion, okay, and if you do a similar expansion, you will find that 1 minus 3 by 4 minus 1 by 4 is 0. Okay. So, the leading order term, the order 1 term is 0. For the order delta term, I have minus 3 by 4 or rather plus 3 by 4 delta eta and plus 3 by 4 delta eta coming from the two terms. Okay. So, this will just be equal to 3 by 2 delta star eta sin theta. Okay. For the radial velocity, I had to go up to the delta square term. The order 1 term and the order delta term were both 0. Okay. For the radial velocity, that is the cross stream velocity. Okay. Streamwise velocity in the theta direction, we just had a velocity proportional to delta eta itself. That also decreased to 0 at the surface. Okay. Okay. So, that is a simplification for the velocities. Okay. We can also simplify the term on the right side here. Okay. We can also simplify the term on the right side, okay, and that is 1 by r square partial by partial r of r star partial t star r star square. Okay. Note that d by d r star is just equal to 1 by delta d by d eta. Okay. D by d r star is 1 over delta times d by d eta. Okay. So, that is 1 by 1 plus delta star eta the whole square 1 over delta star d by d eta of 1 plus delta star eta the whole square d 1 by delta dt star by d eta. And in these terms, this delta eta can be neglected because it is small compared to 1, and I will just get it as 1 by delta star square d square t star by d eta square. Okay. This is the same as what we had for the flow past a flat plate, and the reason it simplifies is because if the boundary layer thickness, okay, if this boundary layer thickness delta, okay, if this thickness delta is small compared to the radius of the sphere, it is effectively like the flow past a flat surface. If the radius of curvature is much larger than the distance from the surface looks effectively flat, okay, and that is the reason that it reduces to the flat the same term, same diffusion term as that for a flat plate. Okay. And then we have to write the expressions for the other, okay, partial t star by partial r star is equal to 1 by delta star dt star by d eta, okay, and partial t star by partial theta, okay, is equal to okay, eta is r star minus 1 by delta. In this expression, only delta depends upon the angle theta. Okay. Only delta depends upon the downstream distance. Okay. So, I can also write this as dt star by d eta into minus of r star minus 1 by delta star square d delta by d theta. Okay. And this is equal to dt star by d eta into minus eta by delta star d delta star by d theta. Okay. So, therefore, my equation, okay, P e by 2, okay, into V r star is minus cos theta minus 3 by 2 cos theta delta square eta square. Okay. That is V r star into partial t by partial r, okay, into 1 by delta dt star by d eta, okay, plus V theta, okay. V theta is equal to 3 by 2 delta eta sin theta, okay. V theta is 3 by 2 delta eta sin theta, okay. Okay. Into 1 over r, 1 by 1 plus delta eta into partial t by partial theta, which is this expression here. Okay. Okay. Into dt star by d eta into minus eta by delta star d delta star by d theta. Okay, is equal to alpha, sorry, there is no alpha because I have already got a Peclet number. Therefore, this is just equal to 1 by delta star square d square d star by d eta square. Okay. So, that is what my equation reduces to. Okay. I can collect some factors on the left and the right side. First of all, there is a 3 by 2 multiplying each of these terms. So, on the left side I will just get 3 Pe by 4, okay, into, if I multiply throughout by delta square, you can see that I will get delta cubed cos theta, okay, minus sin theta delta square d delta by d theta into eta dt star by d eta is equal to d square t by d eta square. Okay. So, this is the final expression. I can take the negative sign in front of this one, okay, and these two will become plus signs. Okay. This is the simplification that we get, okay. And sorry, it is eta square here, yeah, that is what, eta square here, okay. You can see there is an eta square on this term and there is a product of 2 etas in this term here, okay. So, it gets eta square, okay. So, this is the final expression. How do we solve it? I will continue the solution of this in the next lecture. Basically, as you can see that the temperature dependence on eta is the same as for all the other problems. Okay, it is the boundary layer thickness variation with theta that changes. We will examine how to solve this in the next lecture. Okay, so I will continue this calculation in the next lecture. I will see you then.